Hi there, welcome back. This is my channel, a little bit about everything. I've been doing lately a bunch of videos about pumps, and I find the concept, I print them out and see if I can get it to function like proof of concept, right? And this video is going to be about positive displacement gear pump. There are two types. One of them's gear on gear, positive displacement, they're spur gears. I'm assuming they're involute gears. I haven't been able to find any information about what type of gears is preferred in positive displacement pump, but I'm going to do it with an involute gear, spur gear. And there's another type where, when it's gear on gear, one of them is the driven and one's the driver, right? And you put a casing around that, and what happens is, let's say I have gear on top of gear. I would say this is my input and that's my output. Well, you're not drawing material in. If this is the input, you're spinning against the flow. But what happens is, in reality, is the teeth fill up with liquid and they're brought over to the other side of the pump where they go out the output. So you're spinning your teeth against the input direction, right? And there's another type where you only have one gear, but you have a chamber that acts as the second gear. Okay, I'll be doing that maybe in the next video. So let's get started. This is how you're supposed to create an involute gear. Now, certain things you should know is that if you're going to mesh two gears together in a standard inch system, they should have the same diametrical pitch, which is the number of teeth divided by this portion of the circle, which is the pitch diameter. So let's say I had 40 teeth, and I would divide it by my pitch, or my diametrical pitch. Oh, my pitch diameter, excuse me. This is my pitch diameter right here. So if I have 40 teeth, I divide it by my pitch diameter. Let's say it was 5. That would mean I would have a diametrical pitch of 8. And if I was to convert that over to metric, you would take 24.5 millimeters divided by 8 gives you 3.17 and some. That would be your modulus. To mesh two metric gears together, they must have the same modulus, which does not mean they're going to have the same number of teeth. But they do have to have the same modulus. And in a standard system, they must have the same diametrical pitch to mesh together properly. Okay? So what you do is, if you look at these formulas for these circles, right? This is the addendum, or the OD. This is the pitch diameter. This is the base circle. And this is the clearance angle, or the working depth. Now, you're going to find in many references, like as in the Machinery's Handbook, right? You're going to find references and formulas to find these for every size of gear you want to create. So what you do is, once you've got these dimensions, you take and you create these lines. Okay, these are spaced every 5 degrees, and they're connected to the base circle, right? Now, to create this involute pattern, if I take from each of these lines, and these are perpendicular or tangent to this point here, and that line's tangent to this point here, and so forth, all 8 of them, this distance is just this arc rolled out into a straight line. So this will create your involute gear. Now, this pressure angle on this line right here, on the pitch diameter, the pressure angle is 20 degrees. If you want to find the base circle, it's the pitch diameter times the cos of 20 degrees, which is going to give you the base circle off of the pitch diameter. And all this is, see, I wanted to show you step by step how it was created, but I can't seem to backtrack my steps once I've saved it into my, oh, and I'm using Fusion 360. I can't backtrack it. There's no backspace. I can't go into these and show you step by step what went on. Oh, maybe I can. See, these dimensions, if I show you a little closer, the base circumference which was this, is in actuality my base diameter times pi, and if I times that by a fraction, which is these, like these are on a 360 degree angle, so I have divided by 360, and I have 5, 10, 15, 20, up to 40 degrees. This happens to be 35. So my base circumference times this fraction gives me the length of my tangent. Okay? And here, these dimensions, let's say the base circle, it's the pitch diameter times the cos of 20 degrees. And my pitch diameter was a given. Now, if I'm going to do gear ratios, 3:1, and this was, say, 2 inches, I would have to make the other one 6 inches at the pitch diameter to get my 3:1. And here, my working depth is pitch diameter minus 2 times 1.25 times the modulus, or the module. These are, this gear is actually in metric, okay, because I use the module. And the outer one is the pitch diameter plus 2 times the module. That is the addendum, or actually this is the outer diameter of the gear. And as you can tell, they're all tangents, right? And once you've done that, all your modeling lines, you got to make them into construction lines. That way, it doesn't interfere with your model. See? And from here, what you do is you go to spline and you attach these dots, connect the dots together. Dot, 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 all the way down to your working depth. Now at this point, if you wanted, you could make a fillet here. Because on a gear, you don't want any sharp corners, because that's where the teeth are going to break, if ever they break. Because there's nowhere else for the stress to go but into that sharp edge. I modeled this gear, I made a copy and paste, and I gave myself a little bit of backlash space so these could mesh properly if the liquid got warm or cold or whatever during the pumping. With backlash, you're going to give it room for expansion. You won't crack the casing or anything like that. A pump should have backlash, because if anything expands, and if it doesn't expand at the same rate throughout the part, you're going to get stresses in the casing, right? Because the gear is going to push outwards on the casing. This is the casing that I made. That is actually a slot command. If you go into create, you can create a slot from center to center. Okay, so I'm going to try modeling the housing with that. Okay, I'm going to try providing a little bit of backlash, maybe 1.5 millimeter through the casing, so that'll give me 0.75. The printer always lays down a test bead, right, to clean out the nozzle before it starts printing, which is a really great idea. This is all the material used to adhere to the table so it doesn't move around. It's not the bracing material or support material. These are the two gears, and they seem to line up perfectly. So it's like I said, let's say this is the inlet, water comes in here. The pump rotates against the inflow, carrying that water around the edges and out that side, like this. See? So the water would be carried along the teeth. So if this is revolving 1 revolution per minute, and it had a 1-inch diameter, that would mean all along the edges you would have half of pie, a width of 1/8 of material, cubic centimeters or whatever you want. That would be the volume being pumped out the output. Okay. That is the cover of the pump printing right now. It's been printing for 17 minutes, so it's probably a half an hour print job. It seems to me it made 3 or 4 rounds around the print, and it's filling in the rest with what seems to be 45. I've inserted the 2 pins inside the pump, and if I spin one, the other one turns, so this pump is good for the test run. So here we are again in the high-tech facility where we will be demonstrating or proof testing a 3D printed positive displacement pump. We're just filling up the container that holds the high-tech fluid that is needed to make this pump function properly. It's called H2O. So what I've done is epoxied the drive side to the gear, and I'm going to set it on low speed. So it should be sucking in on this side the way it's turning. I'm going to prime it up first. But no, I've got it the wrong way. It's this way. There is water coming out of it. I'm going to try it at a higher speed and hopefully it won't damage the pump. See? It's working. Oh yeah, look at that. So there you go, folks. It works. Woohoo!